A defining moment in a football match. Free kick near the penalty area. All team members need to bond together and work in perfect sync. The player taking the free kick needs to figure out the distance to the goal, the angle at which the ball will swerve, and the force he needs to apply on the ball to beat the defenders. His other team members need to be attentive and agile, awake to any opportunity that comes their way. All parameters must be met to make this into a winning goal. Something similar must happen when atoms bond together. Curious to find out? Keep thinking. Hello and welcome. You may have often heard that a man can be judged by the kind of relations he keeps. Well, atoms sometimes behave very much like people, and by understanding the nature of their bonds, we can get to know them better. In today's show, we will learn about the meaning and significance of bond parameters like bond length, bond angle, and bond enthalpy. We will then learn about calculation of enthalpy of a chemical reaction. Finally, in Exam Decoded, we will undertake the different parameters of exam questions to equip you to face your exams confidently. Everything around us is made up of atoms. So is this ball. As you know, this ball has a fixed radius. Do atoms have a fixed radius? The answer is no. A bonded atom has a different radius from an unbonded one. So what is a bond? You know that in an atom, a positive nucleus holds negatively charged electrons. These electrons are distributed in orbitals. Orbitals are the zones where the probability of locating an electron is maximum. You know that atoms can combine to form compounds. In such a case, electrons are shared and there will be an overlap of orbitals to form a bond. So a bond refers to a pair of electrons shared by two atoms. I have already told you that the radius of an atom differs depending upon whether it is in a bonded or an unbonded state. So, how can we measure the radius of an atom? This can be done by measuring the distance between the nuclei of two adjacent atoms touching each other and then halving that distance. In the unbonded state, the attractive forces are much less and the atomic radius is called the van der Waals radius. On the other hand, bonded atoms are pulled closely together and the atomic radius is called the covalent radius. I am sure you can figure out which of the two radii will be bigger. Since atoms are pulled close to each other, the covalent radii will obviously be smaller than the van der Waals radii. Now, what about different parameters of a bond? Let's start with bond length. In a molecule, the equilibrium distance between the nuclei of two bonded atoms is known as bond length. And as you can see, the covalent radius is half this distance. It's often said that there are no boundaries in friendship. Your best friend may be your classmate or somebody much older. Likewise, there can be a bond between similar or dissimilar atoms. Let's first take a look at a bond between two similar atoms, as is in the case of a chlorine molecule. Here, the chlorine molecule's covalent radius is 100 picometer and its bond length is 199 picometer. Take a look at the covalent radii of other halogens. As you can see, the covalent radius is nearly half the bond length of two similar atoms bonded together. What about the bond length of dissimilar atoms? Let's take the example of hydrogen iodide. Here, the covalent radius of iodine is 133 picometer and hydrogen is 28 picometer. As you can see, the bond length is 161 picometer. That is the sum total of the covalent radii of hydrogen and iodine. I am sure you have all heard of popular characters who formed a unique bond with each other. Charlie Chaplin and the Tramp Kid, the Three Musketeers, or Robin Hood and his band of merry men. As you can tell, sometimes they were just a pair, sometimes a trio, and at other times many people who formed a bond amongst themselves. Atoms too can share one or more pair of electrons. So there can be single, double, or multiple bonds between them. In multiple bonds, the atoms share more than one pair of electrons. Accordingly, the bond length varies with the number of electrons shared between two atoms. As you can see, bond length is longest in a single bond and it is the smallest in a triple bond. And what happens to a molecule when more than two atoms bond with each other? In such a case, bond length will be the distance between the nuclei of the bonded atoms in the molecule. This in turn depends on the covalent radii of the bonded atoms. Now let's move on to another bond parameter, bond angle. We have already seen that bonds are formed when atoms share electrons. If a molecule has more than one pair of electrons, they will repel each other. In such a scenario, electrons arrange themselves in the molecule in such a way that repulsion is minimized. The simplest case is that of a molecule with two bonds. Here, the two pairs of electrons will experience minimum repulsion. The angle between the two bonds is called bond angle. This is an internal angle between the orbitals containing electron pairs in the valence shell of the central atom. For a stable molecule, the bonds should be arranged as far as possible. I am sure you have figured the importance of bonds between constituent atoms of a molecule. They are the building blocks of a molecule that determine the overall structural arrangement of the molecule, a bit like the football team we saw earlier. Bonds between the players determine the overall character and makeup of the team. Let's now explore the connection between atomic radius and bond angle. Here you can see oxygen atom bonded to two hydrogen atoms and two chlorine atoms respectively. In each case, the central atom is the same, that is oxygen, but the bond angles will be different. They will be determined by the covalent radii of the atoms of the other elements bonded to oxygen. Since chlorine has the largest covalent radii, so the bond angle here will be the largest, and since hydrogen is the smallest in size, the bond angle here will be the smallest. Now, how about going to the neighborhood park and catch up with some kids having a good time on a seesaw? But why a seesaw, you may ask? Here is why. As you can see, the seesaw up-down motion is because weight is not equally distributed between our two friends. They are dissimilar. Similarly, in the case of a bond between dissimilar atoms, the pair of electrons is not shared equally. In fact, it is pulled more strongly by the smaller atom. The tendency of an atom to pull electrons towards itself is called electronegativity. Smaller atoms have higher electronegativity as compared to bigger atoms. Since bigger atoms form bigger bond angles, hence we can say that lower the electronegativity, bigger will be the bond angle and vice versa. If we were to compare two molecules with the same central atom bonded to atoms with different electronegativities, the bond angle will be more where the electronegativity is lesser. Now it's time for me to take a short break. But before I go, let's test how closely you have bonded with all that we have discussed till now. Here is your question. Which of the following will have the biggest bond length and bond angle? A. OF2, B. OCl2. So put your thinking caps on and I will see you with the answer on the other side of this break. Welcome back. Before the break, I asked you, which of the following will have the biggest bond length and bond angle? A. OF2, B. OCl2. The correct option is B. OCl2. In this case, oxygen is the central atom in both the molecules. Between chlorine and fluorine, chlorine has a bigger covalent radius. So OCl2 will have a bigger bond length and bond angle. Alright then, we have covered bond parameters such as bond length and bond angle. Now what about the strength of a bond? You can ascertain the strength of an atomic bond from the amount of energy which is required to break it. This energy is called bond dissociation enthalpy. We can also measure the bond energy from the amount of energy which is released when bonds are formed. This is known as bond formation enthalpy. As we know, bond dissociation is an endothermic process as energy is absorbed, and bond formation is an exothermic reaction as it is an energy releasing process. However, if you remember the first law of thermodynamics, you will know that energy can neither be created nor destroyed. It can only be transformed from one form to another. So irrespective of the fact whether a bond in a molecule is broken or reformed, the energy involved will be the same. We can define bond enthalpy as the amount of energy which is required to break 1 mole of bond of a particular type between two atoms in their gaseous state. In magnitude, it is same as the energy released when 1 mole of bond is formed from gaseous atoms. Generally, bond enthalpy values are given in kilojoules per mole of bonds broken. And what about molecules which have more than one bond of the same type? Simple. We work on average bond enthalpies for them. Let me explain it to you through an example. Take a look. Methane has 4 carbon to hydrogen bonds. The first carbon-hydrogen bond is broken from CH4 using a certain amount of energy. Now, the energy needed to break the second carbon-hydrogen bond from CH3 is different from the energy consumed during the first step. Similarly, the energy required to break away hydrogen will be different for CH2 and CH. So for methane, we need to calculate average bond enthalpy. Now, here is an easy one for you. Which would be more difficult to break? A bundle of short twigs or a long dry branch? The answer is obvious, isn't it? Long branch will snap with hardly any effort at all, while for the short twigs, you will have to exert yourself and spend more energy. In the case of atoms too, atoms that are bonded closer have a shorter bond length and are difficult to break. In other words, the bond enthalpy of atoms with short bond length will be more than that of the atoms with longer bond lengths. We have dealt with the energy required to break or form a bond. But when do bonds break? Any guesses? Well, chemical bonds break during chemical reactions. In fact, in chemical reactions, chemical bonds are broken in the reactants and new chemical bonds are formed in the products. So enthalpy of a reaction will be the difference between the energy absorbed in breaking bonds in the reactants and the energy released when new bonds are formed in the product. From transfer of energies to transfer of thoughts, let's see what thought-provoking question our young caller has for us today.
Hi, could you please explain me the role of bond enthalpy in the classification of reactions as endothermic or exothermic?
That's an important concept our young friend has picked up on, and here is your answer. In a reaction, if the products have more total bond enthalpy than the reactants, then the reaction is exothermic. The opposite will be the case for an endothermic reaction. Now, are you ready for solving questions on your own? Because coming up next is Exam Decoded. So, brush up your knowledge while I take a short break. Welcome back. As you know, today we have been discussing bond parameters, and here is a quick recap of all those parameters. Bond length is the equilibrium distance between the nuclei of two bonded atoms in a molecule. Bond angle is the internal angle between the orbitals containing electron pairs in the valence shell of the central atom. Another important bond parameter is bond enthalpy. It can be defined as the energy required to break 1 mole of bonds between pairs of atoms in the gaseous molecule. Finally, we saw how to calculate enthalpy of reaction, that is, the difference in bond enthalpies of the reactants and the products. If you have thoroughly understood these points, no question can baffle you. So get set for Exam Decoded. Welcome to Exam Decoded, your sure shot way to better scores. Before I fire away those rapid fire questions and you shoot back those answers, let me quickly run you through the rules again, although I am sure by now you are well versed with them. 5 questions, 5 seconds for each question, and 1 mark for every right answer. We will then compare scores and see how well you have done. Your first question is a multiple choice one. Bond dissociation enthalpy is always A, positive, B, negative, C, 0, D, unity. If you chose option A, give yourself 1 mark. The next question. Bond dissociation enthalpy is greater than bond formation enthalpy in endothermic reactions. True or false? Once again, the right answer is true. Let us move on to the next one. Bond enthalpy is the energy required to break 1 mole of bond between pairs of atoms in the A, gaseous molecule, B, liquid molecule, C, solid molecule, D, any molecule. I am sure you know the correct answer. It is option A, gaseous molecule. Here is the fourth question. Bond angle is directly proportional to A, van der Waals radii, B, electronegativity, C, bond enthalpy, D, covalent radii. The right answer is D, covalent radii. The last one is a slightly difficult one. Carbon to carbon single bond is stronger than carbon to carbon double and triple bond. True or false? The answer is false. In fact, carbon to carbon triple bond is the strongest. So what does your scorecard look like? If you have scored 5 out of 5, congratulations, you are a high flyer. If you got 4 or 3, you are an achiever. Anything below that means you are a learner. Well, the buck doesn't stop at these scores alone. To score more and excel in your exams, log on to www.topperlearning.com where you can revise and practice till you are perfect. Chemical bonding carries a weightage of 5 marks. This means it is critical according to our weightage meter. Prepare well and you will be able to answer all the possible questions from this chapter. The questions that you can expect from this chapter will mostly be short answer type for 2 or 3 marks. Mainly, they will test your numerical ability and will entail calculating bond order or bond energy. You may also be asked to calculate the bond length based on given covalent radius to measure change in a chemical reaction. It is always good to have an ideal to evaluate your performance with, isn't it? So, let's solve a question and see what the ideal way of answering it is. Estimate the enthalpy for the given reaction for formation of water using given bond enthalpies. H2 plus half O2 gives rise to H2O. Here, the energy of the individual bonds is given. First, we will calculate bond dissociation energy of breaking 1 mole of hydrogen to hydrogen bonds and half mole of oxygen to oxygen bond, which is equal to 436 plus half of 495. Next, we will calculate bond formation of 2 moles of oxygen to hydrogen bonds, which is equal to 2 into 463 kilojoules per mole, which is equal to minus 926. The minus sign indicates that in bond formation, energy is released. This step fetches us another 1 mark. As you know, enthalpy of a reaction is equal to sum total of bond dissociation and bond formation enthalpy. On substituting the values, you will get the answer as minus 242.5 kilojoules per mole. And this final step gets you your final 1 mark. Exams are not just about preparation, they are about smart preparation. So let's see what smart tips our expert has for us today.
Hi, I'm here today to give you some important points from the topic that you have just studied. Firstly, please remember the difference between covalent and van der Waals radius. Secondly, remember, as bond length decreases, bond enthalpy increases with the increase in number of shared bonded electron pairs between the atoms of a molecule. Thirdly, spectroscopic methods are extremely useful in determining the bond angles and also giving us an idea of the electron distribution in molecules. Fourthly, please remember to use the units while giving bond parameter values.
Those were some useful tips to add to your knowledge account, weren't they? Now, the only ingredient you need is hard work. As Mark Twain said, dictionary is the only place where success comes before work. So, work hard, work smart, and nothing can stop you from becoming a topper.